So I'd like to welcome everybody officially for joining us here today for this Passive House Materials and Innovation Workshop. Today is part 2 on mechanical systems. We had an excellent discussion on Tuesday on building envelope systems. For those who missed it, the video recording is available, so you can catch up on that online on your own time. Today, we're going to be continuing the discussion by diving into mechanical systems. Before we get started, I do want to acknowledge, I want to mention that our upcoming Passive House Massachusetts Symposium is happening on Wednesday, November 16th. I mentioned this on Tuesday as well, but those who maybe didn't join us then, just let you know this is happening. Early bird registration is live and open, so if you wanted those discounted registration, you can do that now. You can find out all the information on our website, phmass.org. I also do want to acknowledge MassSave, who are the sponsors of today's event and have been putting on a lot of excellent Passive House lunch and learns and workshops over the last several years. They've now expanded their program to include all electric homes in addition to Passive House. So I did review these incentives on Tuesday, and I'm sure you guys have seen them many places, but just to make you aware, they have the new 1 to 4 unit incentives for going all electric, in addition to the Passive House incentives for multifamily buildings. There's more information about this on the MassSave site, and of course through our site on phmass.org. But please take advantage of these if you're working on any project that is eligible for. They're pretty great incentives for you for projects. With that said, we're gonna just go ahead and get started and dive into what our session is. I told folks a little bit on Tuesday about how this came about. We had a lot of discussions here with some of us on our end about new technologies in regards to today's session about, say, hot water systems for all electric buildings, things that were becoming more readily available, and it led us to kind of a question of, are some of these systems being used in Passive House projects, and what systems are being used? What are folks actually seeing in certified projects? So that brought us to our friends at Hrvs, James Ortega and Al Mitchell, to try to answer this for us. So they did a lot of great research on their certified projects and put together a lot of information on what materials and what systems are actually being used in certified projects, and how has that been changing over the years. So on Tuesday, we reviewed all sorts of different building envelope systems related to wall assemblies, roof and floor assemblies. Today, we're going to dive into mechanical systems, hot water, heating and cooling, ventilation, all these great mechanical features to Passive House buildings. So with that, I'm going to turn things over to Al and James. Just like Tuesday, if you guys have questions, use the chat room. Ask them there. We will have time at the end to unmute people, and you can ask them directly. But during the presentation, just type whatever you have in the chat room, and we'll address it. So James and Al, take over.
Sounds good. Thanks, Aaron. I will share my screen. Welcome, everybody. I hope you're ready for the mechanical systems. Oh, shoot. Aaron, it looks like, there we go. Now I can. Perfect. Okay. Screen is shared. Pull up the chat while I still see that. Awesome. Okay. So yeah, welcome everybody. Day 2, mechanical systems. Buckle up. We'll try and get into this. Yeah, we've gotten our ducks in a row. We do have 2 CEUs for Hrvs CPHCs and other professionals trained by Hrvs available. That's at the end of this session. We will make the code available for the first session to Aaron so that he can update that on the recording. So if you attended on Tuesday and you need CEUs for that session, go ahead and check out the recording after Aaron gets those code CEU numbers from us. So yeah, let's jump right into it. We're going to go through the different types of heating and cooling systems we've seen on different projects: mechanical ventilation systems, domestic hot water. Got mechanical ventilation in here twice. My bad, we're not talking about it twice, just once. Renewable energy, and then we're going to close with a little bit of conversation about the grid and passive buildings in general. Much like Tuesday's session, so just a quick refresher if you guys did not attend Tuesday's session. The way we can look at these different systems and how they're used in different projects is kind of interesting to look at in terms of the different properties that projects have. So first is location. Where are they located? And that question is, we're looking at projects right now that have gone through Hrvs certification, either design certification or final certification from our last iteration of the standard and the current standard. So Hrvs plus 2018 and Hrvs 2021. The projects we're looking at are in climate zones 4A and 5A. So that's first one is where's the location? How does that inform some of these mechanical system designs? The second piece is the building functionality. So what is the building used for? So we're going to be looking at single family homes, multifamily projects, and some non-residential as well as mixed use projects. So that kind of also informs what systems are more prevalent. That really kind of proves to be the most prevalent reason for using one system versus another is building function, which makes sense. And then the last thing we'll talk about is looking at, is it a retrofit project or a new construction project? Because that will also kind of inform those decisions for what kind of mechanical systems are being used. Yeah, I see there's a question in the chat. What is the code for the CPHC learning units? That's going to be at the end of the presentation, so stick around. So the first thing we'll look at is heating and cooling equipment and just looking at what are the most common manufacturers we've been seeing on projects. So by far and large, most passive house projects, FIAS projects have electric heating and cooling systems, and specifically heat pumps or variable refrigerant flow systems, but basically heat pumps in general. So Mitsubishi is the manufacturer we see the most often on all projects across the board, whether it's in 4A or 5A. And then close behind that is Daikin and LG on quite a few projects, but with all of these other manufacturers scattered in there as well on projects that we've looked at. In terms of these manufacturers by project type, so there's new construction versus retrofit in here. And new construction, again, Mitsubishi is kind of leading the way on both of these categories, but on the retrofit projects, it was kind of interesting. There's a Minitere was used on one of those projects, which is a combined device that does both heating and cooling, as well as ventilation with the heat recovery core on it. So we'll talk about that device a little bit more later, but that was interesting that was a retrofit solution for one project. And then I guess we're skipping. Oh, here's the manufacturers by building function. Sorry. Hang on. I'm skipping all over the place. So yeah, manufacturers by climate zone. We covered that one. Okay, here, manufacturers by building function. Must have fast forwarded through that slide. So this is breaking it down into single family projects on the far left, multifamily, offices, mixed use projects, and then school and education facilities. And again, you can kind of see single family Mitsubishi, kind of either a mini split or a ducted Mitsubishi system is really common in single family projects. On multifamily, it's a little bit more varied. We see combinations of mini split versus VRF systems. So that's why you see Daikin in here, LG, as well as Mitsubishi kind of more closely grouped together for multifamily projects. And then offices, mixed use, and school and education are kind of a smattering of each kind of the rest of the manufacturers we typically see. So sorry, again, now by project type, new construction, Mitsubishi, retrofit, also Mitsubishi, but that one case that had the Minitere being used for retrofit was kind of an interesting application that we'll talk a little bit more about later. Now looking at the system types, so whether or not you're using an air source system, a ground source system, a VRF, whether it's ducted, whether it's ductless, et cetera, is so basically most prevalent that we typically see is air source heat pumps with that are ducted. That's the most common that we see both in climate zones 4A and 5A, followed closely by air source heat pumps with ductless. So that would be a mini split situation where you've got a fan coil unit or something like that inside of a system that's being used for air source heat pumps that are ductless. Only a couple of projects do we see using ground source heat pumps, which is kind of a popular, I think, first glance when you're thinking of high performance mechanical systems. You always hear people trying to talk about using geothermal, which they're normally just referring to ground source heat pumps when they're talking about geothermal. But we don't tend to see them on a lot of our projects. I think it really comes down to cost in terms of drilling and trying to, get wells and having the space for ground source. But we do see it occasionally. So that's also listed on this graph. Now by building function, again, single family, most prevalent is air source heat pumps in single family projects. We did have one project with a ground source and one that had a VRF. It was kind of a bigger single family home that had that VRF system. But most prevalent air source heat pumps. Same is true in multifamily. It's basically some kind of an air source heat pump, either a split system or a ducted system. And then on the mixed use, also air source heat pumps most common. And then in the school and the education, VRF is a little bit more popular, as well as a couple instances of ground source heat pumps for both an office and a community facility. New construction versus retrofit. We've only seen ground source and VRF used in new construction. For retrofit applications, it's much more typical to be an air source system, forced air system. And then manufacturers by climate zone for ERVs and HRVs. So this is ventilators basically. And we have a whole bunch of ventilation systems out there that are available. This is by no means an exhaustive list. We've seen other projects with other manufacturers, like Brown is something I see quite often as well now. But of this sample projects that we're looking at, Zender was the most common that we see, and it's probably a majority of those projects are single family that we're using the Zender units, and you'll see that in the next piece here. But yeah, all of these manufacturers are really grouped close together after you kind of parse out the Zender group, which is been long standing. And you can see here, right, in looking at the single family, that is by far and more large the most common ventilation unit that we see in single family. Multifamily is kind of an even split between Panasonics and Zenders. But again, I'll mention that for the offices, it's kind of everybody's trying different things for office and school and education facilities, going from really big units like Train, which is like a rooftop unit, versus again more localized and kind of combined units like the Minutair. Build Equinox is also in here as the yellow, which is the Serve or the Serve 2. And those we've seen used on a couple of mixed use and a couple of single families projects over the past couple of years. The next slide I've got in here. Oh, apparently zoomed in or something. It's not letting me go to the next slide. There we go. Manufacturers by project type. So again, new construction, Zender is more common in new construction, also used quite a bit in retrofits as well. But the next most common we've seen in the new construction group is Panasonics. So this one's, I think it's more relevant to the project type and whether or not it's a centralized versus a decentralized ventilation system, of what type of ERV or HRV you're going to go for. The next slide is looking at that difference. So energy recovery ventilators versus heat recovery ventilators. So for people who aren't familiar, energy recovery ventilators not only recover heat from the ventilation air, they also recover moisture or humidity. So if you're in a very cold climate, like I'm in Chicago, you guys are in Massachusetts, if it's really cold and dry in the winter, you want to try and retain that indoor humidity in the cold season. So an energy recovery ventilator will do a little bit of that and try and keep some of that humidity inside of the home and help try and reduce the really dry air that we get in cold climates like that. So you can see, basically most of our projects are using energy recovery ventilators, whether it's climate zone 4A or 5A, the vast majority are ERVs. That's not to say HRVs are worse by any means. They just don't have that humidity recovery. But what heat recovery ventilators lack in that humidity retention, they typically make up for in having higher recovery efficiency for the heating. So they actually recover a greater percentage of that exhaust heat that's leaving the building. So, typically an HRV can have anywhere from like a 90 to 95% recovery efficiency, whereas ERVs, for heating at least, have a recovery efficiency anywhere between 75 to maybe 85 on the high end for heat recovery. So that's kind of the trade-off you have to make on these projects. Now by building type, we've really only seen ERVs in single families in both climate zones. So the HRVs are a little bit split right between the multifamily and the office type buildings. All the other projects we looked at in this study were using an energy recovery ventilation system. And then new construction versus retrofit, again, vast majority ERVs, but only one project was using an HRV for the retrofit group. Let's see. Okay, talking about domestic hot water. So looking at the different types of hot water systems that we see in FIAS projects. So unless you're doing a FIAS 2021-0 project, you can still technically use natural gas as a hot water device for FIAS core projects. Our one stipulation at this point is that that system has to be electric ready. So you need to provide capacity in the electric panel. You need to provide that, when that system is retired in, 15, 20 years or whenever it's at the end of its lifespan, you're fully ready to bring in a new electric version of that device. So that's just to point out that that's why we have natural gas tanked and natural gas tankless on this list. So that's the orange and the like the teal color. All of the other ones, the blue, red, yellow, and green, all of those are electric water heaters, and it is either an electric tanked, where it's just electric resistance, or it's a heat pump water heater, which is basically using condenser technology to help the efficiency. Heat pump water heaters are, 2.5 to up to 4 times more efficient than electric resistance water heater. So that's kind of the two groups. So we see a lot of electric tanked domestic hot water systems and a lot of heat pump water heaters. The heat pump water heater split one, the green one, is basically representing where the condenser and the water storage tank are separate from each other. So the condensing units on the outdoor side, that's basically the Sandin CO2 heat pump water heaters is what we're referring to for the most part. When it's a split heat pump water heater system. And basically in the Sandin unit, for example, the CO2 is used basically as refrigerant to connect the outdoor condenser to the indoor water heating tank to basically accomplish the same thing as a heat pump water heater, but rather than having them in one combined unit that's inside of your building, it's split into two separate pieces. Now by project type is where we really see the big split between where the heat pump water heaters are used and where electric tanked units are used. And I see a question in the chat, which I do want to answer real quick. Yeah, so the question in the chat is, have we seen solar assisted heat pump water heaters used as a split system? And the answer is yes, but I haven't seen one since 2014. Basically, I think they're good. Like in general, I think it's a good idea. It's another way to harness the sun's power to help reduce energy use in the building. But the drastic cost reduction in photovoltaic systems over the past 10 years or so has basically made it an easy value engineer, where it's like, okay, we could do this solar hot water system, which costs this amount of money, or we could do 15 solar panels for the same amount, right? And at this point, it's like, as a cost saving measure, that's kind of what people have been doing instead. Is okay, we're going to reduce our energy use, and then at the end put renewables on top of the building. So going back to this breakdown though. So for single families, the vast majority are using heat pump water heaters. Only a handful are using the electric tanked water heaters. Multifamily is kind of the opposite end. So a lot of them are using electric tanks or natural gas systems. And typically the natural gas systems are these big centralized, like a lock-in bar, centralized water heater or something like that for the multifamily buildings. Just because a lot of project teams that are working on projects are using engineers that have been doing natural gas water heaters for the past, 40 years of their careers. They're not looking to switch it up at this point yet. So we're starting to see those phase out, especially since we've included in FIAS Core 2021 that you need to have electrification readiness as part of that standard. So I imagine we're going to start seeing natural gas slip out of these projects more frequently as we move forward. But that's kind of what's available for multifamily at the moment. I think Al might mention a little bit later about some of the other newer heat pump water heater, like the split systems that we're going to start seeing from multifamily in the future. But I'll leave that for Al to talk about later. And yeah, okay, great question in the chat as well. Are the electric tank systems central or in each unit? That's a good question. So when we're seeing the electric tanked stuff in multifamily, typically it's per unit. They're, for the most part, decentralized electric water heating in those multifamily projects. More often than not, it's a centralized natural gas system rather than a centralized electric tank system. It's just, I don't know why that is exactly, but that's typically what we see. Yeah, so that one's pretty interesting. And then as far as new construction versus retrofits go, retrofits, the majority of them are using heat pump water heaters. Only one of the projects we looked at had an electric tanked one. But the same trend holds true for new construction as it did for all the other ones, where the top two are electric tank systems and heat pump water heaters. I'm personally kind of fascinated by the tankless systems out there. So like both electric tankless, and I know there's natural gas tankless systems. I would have loved to put one in my apartment. I live in a condo here in Chicago, but our electrical panel service isn't high enough. So our whole building would actually have to upgrade service if we wanted to do an electric tankless. So it's just one of the upfront considerations that I think project teams have to consider when they're doing tankless systems. I will mention back on this one, so that the office project we saw that used electric tankless, basically it came down to the distribution of their bathrooms was so far apart that it just didn't make any kind of sense to have to run domestic hot water piping all the way to these individual bathrooms. So they, instead of having like one central tanked electric water heater, they opted for like 4 little tiny electric tankless systems that they just put right beneath the lavatory in those bathrooms in that office building. So that's kind of like, that's the application that I've seen most frequently, is when you've got kind of spread out, you know, pancake-like buildings where the water heating is really far distributed. Okay, now looking at manufacturers. So again, we see a whole ton of different manufacturers used on projects across the board. So A.O. Smith is by far and large the most frequent type we see. And they actually make both electric tanked and heat pump water heaters, which is kind of why we see that overlap that, you know, that happens pretty frequently. It was kind of interesting to me that this was kind of a split between climate zones. So A.O. Smith was really popular in 5A, but Bradley, White, and Rheem were more popular in climate zone 4A. Rheem is also popular in 5A as well. That's another common brand we see. But that was kind of an interesting split when we were looking through this. Oh yeah, good question. What brand or type would I have used for my condo? So I'm pretty fortunate. My whole building is all electric. We don't have heat pumps though. We just have electric resistance baseboards in our building. So if I was going to choose a brand for my electric tankless system, I think I hadn't really even gotten that far. We just had to first look at the electrical panel to see how it was. I didn't even get to the point where I was looking at brands, just because it was completely out of the picture. So we'll maybe talk about some brands out there at the end of this one. Okay, so by building function then. So again, single family, most common brands we're seeing, because again, heat pump water heaters are the most common in single family, were the Rheems and the A.O. Smiths. Multifamily was also A.O. Smith, but rather than the heat pump water heaters, there's more frequently the tanked electric A.O. Smith units that we saw in those projects. Same was true in the school and education facilities. A.O. Smith was pretty common for their tanked electric water heaters as well, or sorry, for their heat pump water heaters in the school and education facilities. Okay, and then by project type, so yeah, new construction, kind of the same trend. Basically, both the A.O. Smith and the Hrvs are the most common still. And in retrofit, A.O. Smith was pretty common as well. Okay, the next one we'll talk about is something that we have a lot of conversations with project teams about how they do distribution for domestic hot water systems. In pretty much all of the projects we see, FIAS has a prerequisite requirement for zero energy ready homes that they need to meet this water sense test, which is basically the concept that you don't want to waste water when you're turning on your hot water tap. You want to get hot water very quickly is the idea, right? So there's this time to hot test that all of our projects have to pass. And the solution for that oftentimes is to include domestic hot water recirculation. So one of the requirements though of that hot water recirculation is that it has to be on demand. And on demand means you either have one of these smart recirculation pumps that kind of learns what the occupants of the single family home, for example, are doing. And it knows, okay, every morning they're going to work at 8 a.m. So it's going to start up the recirculation system at like 7:45 so that you have hot water by the time you're going to take your shower, for example. Or you can treat on demand as just a pressure drop in the system that will trigger the recirculation pump to start running. That's the more common one we see in multifamily projects. But basically the DHW recirculation stuff here is just listing all of the different brands of recirc pumps that we've seen, and all of them have the capability at this point, I think, to do that on-demand recirculation, which is pretty critical. And again, on demand as opposed to continuous recirculation or time-based recirculation, which was much more popular, maybe 15 or 20 years ago. But that was basically the concept that, okay, people want hot water. We don't know when they're going to want it. So we're just going to run this pump 24/7 and run hot water throughout our buildings. It's kind of a big waste of energy. So these on-demand systems prevent that additional pump energy and also the hot water losses through these lines. So Bell and Gossett, EcoCirc, Grundfos, and Taco, or Taco. I don't know how to say it that well. I think it's hilarious spelling either way. But those are all common brands. And then the last one is NA, because there's a big chunk of projects we see that don't even require this on-demand recirc because they've got a compact design. They're going to meet that water sense test without the recirculation. It's basically having better location of your domestic hot water tank or your system in comparison to where the fixtures are. I think typically as a rule of thumb, if your fixture is maybe more than 50 feet away with a 1/2-inch pipe, you're probably going to need a recirc line because it's going to take too long for it to get hot water out of that tap. So you can see in general here, so under single family and multifamily, it's the most common to not need a recirc, even in offices as well. It's the most common option is that you don't need to include a recirc system. And then the most popular brands we're seeing currently of actual recirc pumps are the Taco pumps and the Grundfos. Those are the most common that we see in most of our projects. Okay, yeah, and then I have a question in the chat, which I think is relevant. I'll maybe go back up. Let me finish pumps and then I'll come back to that question in the chat about heat pump water heaters. So the last slide to look at about recirc pumps is new construction versus retrofit. Retrofit, it is more common that we have to see the recirculation pumps as compared to the new construction projects. And it's because on quite a few of these retrofit projects, they're trying to use some of the existing piping if they can. And because the layout of most of these buildings was already established before they came in to retrofit them, trying to meet this time to hot or reduce the amount of wastewater in those projects. a lot of times they're turning to these recirc pumps to meet that testing requirement. So that's kind of why we see not as many not applicables in the retrofit categories we do in construction, when you can actually design your system, where your piping is closer to the fixtures. So there's a question in the chat: is what is the feedback from owners for heat pump water heaters in cold climates, stealing heat from the interior with loud fans, moving air inside the home? So just a general overview of how heat pump water heaters work is that this is exactly true. So basically, a heat pump water heater is having, and I'm talking about the combined units where the compressor and the water tank are in the same unit as opposed to split units. But the way they work is that they pull in air from the surrounding room, typically mechanical closet or wherever they are, mechanical room. They pull in air to help preheat the water, and basically that's how they get their efficiency. And then they reject even colder air, basically. So in the summer, those types of devices actually help cool down the house a little bit, which is a weird way to think about it, right? Because it's pumping out cooler air than it's bringing in. But in the winter, it does the same thing. So it's actually increasing the load technically on the heating system during the winter. So anecdotally, I think the feedback we get from owners is that we try and teach in our trainings, and as rule of thumb, don't put the heat pump water heater directly next to bedrooms. They are decently loud. Or if you do, you're going to really probably get complaints, or you're going to want to insulate those mechanical rooms really well with sound attenuation insulation. But yeah, they can be noisy. They do make the air colder. We've seen a couple of projects, teams that have, to reduce this potential where it's loud and getting kind of colder air in the winter. We've seen project teams where they duct the mechanical room with transfer fans to another space in the building. Sometimes we'll see the mechanical closets in the basement, for example, and we'll see ducting happen where, they'll have a transfer fan pushing that air up into the attic. So in the summer, for example, you're bringing cool air up into the attic, and then it's kind of falling down the rest of the house. And we've also seen the reverse in the winter where, you're getting cool air in the basement. You're trying to get that distributed through the house. So it's not just a big cold sink at the bottom of your building. Good question. If you put a heat pump water heater in the basement in a retrofit situation, is there a minimum temperature the basement would need to be for the unit to be efficient? Is it a 50-degree basement too cold? Well, this is a good question. There probably is a minimum temperature. I don't know what it is off the top of my head. But we do have a deration protocol that we use based on what the temperature where the heat pump water heater is located. Like, they're designed to be in spaces that are room temperature, like 68 to 70 degrees. So that's mostly what their efficiencies is based off of. As soon as it starts to get colder, obviously their efficiency drops a little bit. They work very similar to an air source heat pump, where at 47 degrees, an air source heat pump for heating can be like a COP of like 3 to 4. But when it drops down to like 17 degrees, it basically cuts in half, down to like 1.5 to 2.5, something like that. So heat pump water heaters work kind of similar to that. I think it wouldn't be as extreme if there's only a 68 degree to 50 degree difference, as opposed to like 47 to 17. But I think that's kind of the general idea there. The next one we're going to look at here is range hoods, very popular subject for above cooktops. And basically we're looking at the differences between direct exhaust, a recirculation range hood. The not applicable cases are strictly the non-residential projects that we looked at that just didn't have a commercial kitchen. They didn't have a residential kitchen. They just didn't need a range hood at all. So the NAs are just referring to the school and community centers and the office buildings that didn't have an actual cooktop. So I think it's pretty interesting to see that a lot more projects in 5A were using recirc than direct exhaust. And there's a little bit more of an even split in 4A, which, makes sense, because when you introduce direct exhaust into a project, you're increasing the amount of losses through the ventilation system. So in colder climate like 5A, it's bigger penalty basically when you have direct exhaust towards your heating losses than it would be in 4A. In terms of building function, it's even kind of more drastic. In multifamily projects, it's much more common to see recirculation than it is to see direct exhaust range hoods. But in single family, again, it's a little bit more even of a split from what we've seen over the past couple of years of projects. I will point out that one of the other prerequisite programs that CS relies on for indoor air quality is Indoor Air Plus, which is another government program. And their version 2, I don't actually know when that's actually officially going to come out, but they had proposed it to come out in 2020. But obviously the whole world had different ideas about what was all going to happen in 2020. But their Indoor Air Plus version 2 will actually require direct exhaust range hoods for all single family projects. So that's coming in the relative near future. So if we looked at this graph again in 5 years or so, the direct exhaust to recirculation range ratio in single family projects would be much, basically be the opposite of what it is for multifamily. We're going to see many more direct exhaust required in single family in the future. Multifamily recirculation range hoods are more common. And I think it comes down to two things. It's basically that direct exhaust requires more penetrations in the envelope. So if you're trying to make short runs for your direct exhaust out of your kitchens for a multifamily building, typically the way we've seen project teams do it is to just go straight out the sidewall, and having that many more holes in the envelope is not necessarily something that's conducive to a really airtight building. So we haven't seen a ton of projects do direct exhaust for recirculation. Question in the chat: do any manufacturers make HRVs dedicated for exhaust hoods? Not that I know of. So all of these projects that we have for fresh air ventilation through the mechanical system, we require you either have direct exhaust or a recirc range hood with it. And the main reason for that is you don't want to use primarily your ERV as the exhaust. Yeah, exactly. In the chat, Alex, good point. But you don't want to use your ERV for the exhaust, the only exhaust in the kitchen, because you're going to grease up the core. And yeah, it's a fire safety hazard, basically. So you're gonna clog up your core. It's a fire risk, and range hoods are, that's exactly what they're suited for. They're supposed to be able to pull out grease and cooking smells and stuff like that. So, and the airflows are much higher for a range hood than they would be for an ERV in the kitchen. For the most part, you're talking a minimum of 100 CFM exhaust through a range hood, and some of these single family projects with big kind of commercial grade cooktops we've seen have had like 200 to 300 CFM range hoods, sometimes higher. All of those require makeup air so that they don't depressurize the building. But yeah, it's definitely a good question. Next slide we're going through here is by project type. So new construction versus retrofit. Again, recirc is more common, but we will start to see more direct exhaust. Okay, next question is about clothes dryers. So I broke these out pretty. I could have just done ventless versus vented clothes dryers. That probably would have been a lot easier. But basically, electric exhaust dryers are the red ones. Those are the only ones that have direct exhaust to the exterior. All the other ones, condensation, heat pump, and hybrid heat pump dryers, are ventless dryers. They're just relying on heat pump technology or condensation technology to take out the moisture from clothes and then not exhausting it directly out of the building. So basically, we most commonly see ventless dryers. That's just across the board, the most common. And in the not applicable cases, similar to the range hoods, those are typically for the non-residential buildings that didn't have dryers in the first place. Yeah, Hank has a question in the chat as well about the energy penalties of direct exhaust. Do many have preheated makeup air? This is a good question. So the energy penalties of direct exhaust are basically that you're exhausting separately from your heat recovery or energy recovery ventilation system. So that air that's being exhausted from the building needs to basically just be brought up to temperature with just the heating system by itself. So rather than recovering some of that heat from that air, it's all going directly out of the building and you need to make up that heat. Some of the units have preheated makeup air, but not all of them. Typically dryers, we don't see having preheated makeup air because when the dryer is running, it's actively producing heat in the space. So any makeup air you'd bring in, you just bring in near the dryer and that would kind of take care of it. We see them more commonly if you've got a really substantial kitchen exhaust range hood. We'll see sometimes preheated makeup air for those systems. And in general, we don't see them on single family homes that often for preheated makeup air. We will see them more frequently for multifamily projects if there's additional direct exhaust separate from the laundry or the kitchens. So oftentimes we'll see, trash exhaust in the trash rooms, and oftentimes that'll be pretty substantial. So they want to preheat that makeup air rather than dropping, 400 CFM of direct outdoor air on somebody. They're bringing that through a preheater most typically, or a post heater, depending on the setup of the system. Okay, closed dryers by types. So condensing and heat pump and hybrid heat pump dryers are more common in single family than electric exhaust. There was literally only one project that had electric exhaust in the single family group. It's more common in multifamily. And I think this kind of comes down to availability of appliances. Specifically in multifamily, a lot of times we're seeing centralized laundry rooms where they need to have coin operated or card operated laundry. And we just don't have a ton of ventless dryers available that have that all set up and ready to go. It's much more frequent that we'll see, electric exhaust dryers that have coin operation, like just available as a commercial option for those multifamily projects, which is why we have a tendency to see more electric exhaust in multifamily for the most part, I think. Obviously, we do still see a ton of heat pump and hybrid heat pump dryers in multifamily projects as well. But for the most part, it's not as one-sided as it is in the single family projects. New construction versus retrofit, kind of the same grouping here. Only one retrofit project had electric exhaust though. So that was kind of, it's pretty clear that it was more common to do a hybrid heat pump or a regular heat pump dryer for retrofits rather than the electric exhaust. All right, Al, we want to talk through some mechanical stuff, or I can open it up for more questions if people have any.
Yeah, we can look at some questions here. Alex has got a comment in the chat. Direct exhaust health benefits outweigh the energy cost. Ways to be efficient and preheat and bring the fresh air very close to the range. Yeah, I think and he mentions Joe Steebrook's presentation on that, and there's a lot of with that, just trying to keep that makeup air for the range hood extremely local to that, so that it's not mixing too much with the space air. We've seen a couple other innovative things with different kind of preheat. Some people will do a preheat solution. Other people I've seen have a damper elsewhere in a mechanical room somewhere that'll just open and depressurize the building when you're doing direct exhaust, and it's in the mechanical room, so it's going to be heated by that equipment. Anyways, yeah. So if you can get it closest to the range, that's probably the most convenient.
And I have one more comment to add
Yeah.
too. Yeah, I think if you had looked at this graph 10 years ago, you would have seen almost no direct exhaust kitchen range hoods. Like basically all of our projects early on were using recirculating range hoods. And I think this shift of people's, understanding about indoor air quality is kind of reflected in this graph that shows the single families. I mean, it's pretty close to even at this point, and it's definitely trending towards more direct exhaust, which I think from an indoor air quality perspective is important to keep in mind.
Yep. Any other questions on the data stuff? Because if not, we'll go into just a couple sample comment or kind of clever mechanical things that we've seen on the next slides. All right.
Can I ask a quick
yeah.
question? Sorry.
Yeah.
Is there a big energy use difference between the condensing dryers and the heat pump dryers?
All the heat pump dryers are the condensing dryers typically. I've not seen an electric resistance condensing dryer. Have you, James?
No, I think basically from what we've seen, the combined energy factor, the CEF, which is what they use as the metric for efficiency for those devices, is pretty similar across the board, whether it's a hybrid heat pump or a heat pump dryer. It's just literally technically what it says on the Energy Star like rating of that device itself, whether it's condensing or a heat pump or a hybrid heat pump dryer. I think the hybrid ones might use a little bit more electric resistance, but I'm not actually sure. And I've never used one, so I don't even know like the difference in like quality of how dry your clothes get. Because I know in the early days that was a big kind of annoyance with homeowners about like, okay, my clothes are like still wet. And it was because they were using these small compact condensation dryers and putting like the load that you would have put in like a natural gas dryer that was built for, twice as much laundry. So anecdotally, I knew that was an issue in the early days. I haven't heard that as much in the last couple of years. I think the technology is catching up and they're getting bigger dryers that can use this technology as well.
Thank you.
And then we got a question in the chat here: to what extent can boost mode work for exhaust? We see a lot of projects, especially those that have on the single family, where they'll have some kind of a fancier unit like a Zender to go into boost mode when the kitchen kicks on or something like that to kick up the flow rate. And some of the units as well on either the larger units that we'll see do a small group of apartments on the multifamily scale will have twin motors. And then same thing with the Zender type unit, is some of them have an auto balancing function, and people have actually been able to rely on their ventilation unit to provide a little bit of that makeup air by unbalancing its flow when activating a direct exhaust kitchen range hood. So there is a possibility there. It's a little more complicated to get the controls to work out okay, depending on the type of units and trying to get all of them to talk together. But it's definitely a valid solution in that regard. So I went through a couple of our projects and pulled out, like I had said, some mechanical designs that were either really good, interesting, or stuff that we very commonly see. On the screen right now, I'm showing a non-residential project that has a recirculating VRF fan coil. So there was one central outdoor unit that was running a bunch of smaller indoor fan coils, and they were recirculating within their spaces. And then there was a centralized ERV, and that's the green line there, that was ducted right into the return of that fan coil. And we've seen this as a way of trying to save on ductwork and combine the two. Much more common in the non-residential projects, and that's simply because if this were to be in a residential project to meet the requirement for continuous airflow in the space, you always have to have that fan in the fan coil pushing some air through to get the outdoor air to where it needs to go. So it's a little bit of extra fan energy if you're going to use this type of setup in a residential project, but again, we don't see too much of that, and I can dive in a little bit more. I've got some samples of what we typically see there. So for a non-residential, if you want to combine the two into this works really, really well. And then it is just a discussion of the controls and how to interlock the controls to make everything work out okay. On the next slide, I've got another project that is a non-residential project. And this is a diagram from their mechanical plans where instead of just dumping the exhausting outdoor air directly from certain places, or sorry, exhausting air from bathrooms and kitchens, and then just dumping the supply outdoor air into the return of the fan coil. This project pulls the supply and the return, pulls the outdoor air and the exhaust air from the return duct of this fan coil unit. This is fairly uncommon and again would only really work well in a non-residential situation where you don't need continuous outdoor air. And it's essentially bringing in one of those packaged rooftop units with the ERV coupled to a heat pump. It's bringing that inside as two separate pieces of equipment. It's less ductwork than having run a separate thing. You're preconditioning that outdoor air so it's not cold, and you can maybe back off on the recovery rate of an ERV a little bit. But again, if this were in a residential project, that fan coil would have to keep running consistently. On the next slide, I've got a little bit more information about what we typically see in a lot of multifamily projects. And it seems like there's a big push for either localized heads or fan coils. Either it's a centralized VRF system or everyone has their own compressor on a roof or on a balcony, depending on the scale of the project. The larger the projects, we will see more centralized mechanical equipment. But on a lot of the multifamilies, especially out in New England, we're seeing a ton of centralized ERVs just driving that. I think James's data showed that, where we've got a centralized ERV on the roof and it's going to supply outdoor air in the green to each of these units. And then there's another exhaust riser that runs back up to that ERV in orange that's going to pull all of the exhaust air from the kitchen and the bathrooms. Again, it's a little less ductwork if you're going to go with a ductless unit, and it works well in these studio apartments shown here. A more complicated apartment with a couple rooms in it will probably need some kind of a ducted system. And then also with this, some people still want to precondition that outdoor air, depending on the recovery efficiency of the unit, the sensible recovery efficiency of the ERV. You could be supplying air that's either that's too hot or too cold for the space into there. So working out the math on that to figure out, try and not supply air less than 60 degrees Fahrenheit to the space would be ideal. If not, a lot of the project teams have decided to put a duct heater powered by another heat pump on the roof, and that'll heat the supply air or cool the supply air, or maybe even a little dehumidification of the supply air from the ERVs, is to not throw off the space thermally, the space air temperature thermally. On the next one here, I've got another image of when we see more of a multiple bedroom type unit, we'll see a lot of these ducted heat pumps. This one here is a centralized VRF system as well. And then the supply duct I've highlighted in red to show that it's supplying space conditioning air to each of the bedrooms. The outdoor air as well has been highlighted in green to show, again, distribution to the bedrooms. And that is a requirement for the FIAS program, is to supply outdoor air to each of the bedrooms in a dwelling unit. And then we've got localized direct exhaust back to that centralized ERV through a grill in the bathroom and a grill in the kitchen, which would imply a recirculating range hood here. And this team as well has got a centralized exhaust in the apartment, and that might be a valid strategy depending on if you can do door undercuts or some kind of a transfer grill situation, and you can save on the return duct by returning out of that little hallway there. Again, the similar concerns about preconditioning outdoor air exist in this project as would other projects with the centralized ERV system. On the next one, James had alluded earlier to a retrofit project that used some of those combined humidifier units. If you want to know more about these things, Alex is in the call, and he's a fantastic resource for humidifier, and will tell you everything you want, everything you could ever want to know about it. And I have an image of it on the next slide we'll get to in a second, but for those not familiar with this, it's a combined unit that uses a heat pump to do heat recovery when it's ventilating, and then we'll also go into a recirculation mode. And when it's in recirculation mode, it'll provide standard heating and cooling for a space, as well as dehumidification. They're a little smaller in capacity. They're only about a ton, and they have a slightly smaller heating size, but you can boost that with either an electric resistance duct heater, or there's a hydronic one as well if you've got a DHW system that you want to feed hot water to that coil. So the thing that is extremely convenient about these is they're a fairly compact unit, and they manage the heating, the ventilation, and the air conditioning all in one. So there's only one piece of equipment rather than trying to interlink multiple systems. But the con is that it is a little bit small in capacity with their current model for some projects. So in this project, it worked out just fine. On the next image, I've got on the next slide, I've got just an image of the unit here. They're fairly compact and flat, and there's plenty of places you can squeeze them in. And I think that in this retrofit situation is one of the reasons why these were considered was their compactness. On the next one, I've got just two DHW ideas that I've pulled out that were uniquely combined with mechanical systems. So the one of them here is from a project, one of the non-res projects earlier that already had a ground source heat pump system going on, so water to water. And they're using a desuperheater, which recovers heat on the ground loop side of that to preheat some of the water, as well as the heat pump itself is heating the water in this preheat tank. And then there's an electric resistance water heater as a booster. So with a lot of the projects trying to electrify a DHW setup, you've got a need to hit that water heating set point of about 140. A lot of heat pump based water heating equipment on the mechanical end of things are at that scale, can't necessarily do that. So we'll see either this post heating tank like they've used on this project, or we've also seen people use a water to water heat pump in series with the water to water heat pump. So we've got an ability for it to boost temperature even further as they're built up in series. So that's still sort of an experimental thing that we've seen just on a couple projects, but this type of system with like an electric resistance hot water heater as a post heater is fairly common as well. Again, it's efficient. With the desuperheater, you're recovering the waste heat, but it is just more equipment in there rather than some type of a package to maintain. The question in the chat: don't do Minotaurs do dehumidification too? Yes, they do manage dehumidification. I think as well as the ventilation and heating and air conditioning. So it does. I guess we need to add another letter to HVAC, HDVAC. I don't know. On the next slide, I've pulled out another type of system. This is an image of a Mitsubishi Qav system. It's very comparable to the Sandin or any of the other heat pump water heaters that we're seeing with the split system. And when they go split, a lot of these are going to be CO2, which is R744, and that's using CO2 as a refrigerant rather than a traditional R410A or what other common refrigerants are. R134 I've seen on a couple of pieces of equipment still. Now, those are all fairly high in global warming potential, GWP. R410A is 2,200 times worse than that of CO2. So by using CO2 as a refrigerant in this, in case you were to ever have a refrigerant leak, you're definitely reducing the total global warming potential life cycle of this mechanical system. And just another point, we as a group, the mechanical engineering side of building things has become more concerned about the embodied carbon within their systems. And based on some of the current available research we've done in that field, mechanical systems make up anywhere from 25 to 40% of the embodied carbon within a building. And the refrigerant makes up about 7% of the life cycle global warming potential within a building as well. So that is a concern as we look into mechanical equipment. Now with the CO2 refrigerant as well, right now we can only use it for heating water. That's the only technology that's available, as well as it's incredibly efficient at low temperatures, which is good for those of us in 5A and 4A like Massachusetts. And then these are a much more kind of straightforward system where there's an outdoor unit and then there's an indoor storage tank, and you have to pipe water between the two. So instead of refrigerant or CO2 in this case is the refrigerant coming inside the building like you'd have with the split VRF system, all of the water heating happens in the outdoor unit, and that hot water is piped into the tank on the indoor unit. And then this is very comparable to the loss efficiency was in fact, for heating, the CO2 is significantly more efficient than a traditional R410A might be. So for example, a typical heat pump doing space heating might make about a COP of 4 at 47 degrees, somewhere in the 2 to 2.5 at 17 degrees, and about 1 at 5 degrees Fahrenheit. A CO2 water heater at 45 degrees will have a COP in the 5s. And then they're able to maintain a COP of about 2.5 down to minus 40 degrees Fahrenheit. So it's their efficiency curve is spread out much wider, and they're much more efficient at heating that water. So that's why, and I've talked to Alex about this as well, is like with the Minotaur type thing where they're doing that for the primary heating and ventilation. If they've got a CO2 water heater as well, there's a hydronic duct heater that people will put on, and it'll take heat from that. And if you've already got this thing that's making hot water incredibly efficiently at low temperatures, you're able to use that to heat your space as well. So there are, and that's more of a single family size system. It could be scaled up, but so yeah, it is a really kind of exciting breakthrough in domestic hot water technology.
We don't have a slide on this one, Al, but can you talk a little bit about some of the other stuff, like maybe drain water heat recovery, and if we've seen that often? I know Hank had asked that.
Yeah.
When we were putting this session together originally.
Yeah, we don't see a whole lot of drain water heat recovery. I think it's a scale size as well. Individual unit-based drain water heat recovery to me doesn't make a whole lot of sense. It's a lot of cost for very little benefit when it only works when you've got someone taking a shower or washing dishes or something like that in their unit. At a building scale, I'm much more interested in it, because you've got one piece of equipment that's maintained in a mechanical room. You can recover all of the heat leaving the building through the drain water as an aggregate and use that as a preheat for incoming water for domestic hot. So like the previous one I had shown where they've got a de-superheater where they're recovering heat on the ground loop side of that heat pump. This is just another way to do drain water heat recovery. I think would be another smart way to do that, where you've got where you're recovering heat and just preheating that incoming hot water, so that your delta temperature you have to make up for from an active heating system like the heat pumps or like electric resistance has to do much less work to get that water up to the temperature it needs to be at. On the next slide, I think we've got some information about renewables. We'll let James cover, and then I'll jump back in and we can talk about the grid. Does anyone have any questions on some of these little mechanical layouts we've just shown in these past few slides? Tim McDonald's within a pipe system. I've only seen it on Tim's project, and I just haven't seen it enough or heard enough feedback from it actually installed to really really make a justifiable call on that. For people not familiar with Hank's question, there's let me find the name of it. It's in one of my notes here. Tim McDonald of Onion Flats in Philadelphia uses a bunch of these pipe within a pipe system. So there's pipes. So the recirculation pipe is running within the supply pipe. It's called the Viega, Viega Smart Loop internal recirculation system. So the recirc line is in the middle, the supply is around the outside, and then it's, instead of having two separate lines where you've got two separate water heating lines where you've got heat loss to either side, this is all within one. I'm not really sure. Again, I think it's a cost thing that's probably going to drive this. So the breakthrough become the norm in upcoming years for logical reasons. Yeah. James has shared a link to it in the chat. Yeah. We need more people to try it. And then we can get good data to see if it, if it is making the impact. The general need for dehumidification in multifamily units. Yeah. So humans are really good at putting out about 400 to 500 BTUs an hour, and about half of that is latent gains. And when you've got multifamily units, which are typically much more dense than a single family home, you've got a lot of humidity buildup in there. And then when we've got the really airtight enclosure, there's less infiltration to manage any of the dehumidification that's naturally been managed traditionally. And then on top of all of that, when you're going into a passive building, you've reduced the heating and cooling loads so much that the equipment is smaller, and in a multifamily especially, the equipment is fairly small and doesn't run as frequently, and then therefore you don't get a whole lot of dehumidification out of that. We're pushing the sensible heat ratio much further down. So in a traditional building and the systems that respond to it can sorry, need some water. So the traditional so in a traditional building, you'd have a sensible heat ratio of about 70%, where 70% of the space conditioning load is sensible dry bulb temperature management, and the other 30% is dehumidification. Because we've eliminated a lot of the sensible loads in a passive building, we're looking at a sensible heat ratio of more of about 45%. So the equipment that we have currently doesn't necessarily respond to a lot of that, and that's where we need something with a dedicated dehumidification. So we've seen a fair amount of interest in this, and on single family homes we'll see a lot of the dedicated dehumidifiers go in if that's a concern, like a Santa Fe whole house dehumidifier just built into the system that'll recirculate air and dehumidify it as needed. For multifamily buildings, we see a lot of this covered by some of the smarter ductless units where it'll run in a dehumidification mode. But that is a good thing to be concerned about when you're designing for that scale of building, is what am I going to do to manage all of this humidity? Can we describe and speak to serve units? So there's another unit out there called the CERV, made by Build Equinox in Urbana, Illinois, and it is an ERV type unit as well that uses refrigerant. It's fairly similar to a Minutair in that kind of core function that it's using refrigerant as its heat exchange method between the two. It can provide dehumidification as well, and a little bit of space conditioning. I think the Minutair seems to be more aimed at the space conditioning replacement fully, while the Serve doesn't quite have that capacity. We see a handful of them on some single family projects, and they seem to work really well, covering the loads in the shoulder seasons as well as some of the peaks in the heating season, but there still is a need for a separate heating and cooling system typically with that type unit. Well, with the Minotaur, we've seen that as almost a replacement for the whole thing. So just to wonder if you looked at traditional solar hot water for multifamily, less complicated, more efficient, and do not use refrigerant. Yeah, we don't see a whole lot of it on a lot of our projects with the solar water heating. I understand it's highly efficient and it's a great way to preheat it, but it's usually the issue is then you have to have a lot of storage so that you have hot water ready for the times where you need it. So it could work well if you're trying to keep a lot of hot water in a tank. And then you've got some kind of a post heater still to make sure you're hitting that set point. There are a few hybrid heat pump water heaters that have an integrated solar heating system as well. Again, it's just not very common, probably cost. And then the other issue with putting more things on the roof is there's more maintenance where someone's going to have to come out there and sweep snow off of it and make sure the reflector is clean and shiny and not dirty. So it's something worth exploring, especially if your analysis shows that you can get enough gain from the solar water heating to make it worthwhile. But then it's a discussion with the building management or the homeowners of how do you maintain the system and how are you going to keep it functional when you need it.
Yeah, I have one
Yeah.
one thing to add there too. I mean, the other thing with solar hot water that we, that again, it's been years since I've seen a project go through with it. But generally it can cover about 40 to 60% of the domestic hot water load with the solar hot water system. But that still means you need another system to cover the other potentially 40 to 60% of the domestic hot water as well. So if you're, it's cost prohibitive in a lot of projects, I think, because you're essentially needing to buy two systems if you're gonna do that. While it's more efficient, it doesn't necessarily cover the entire load. And then, when the sun's not shining, like Al said, you need to have a lot of storage to meet the loads when it's dark.
Any more comments on this portion? We can always come back to this later too if anyone has another thought.
There's one more in the chat.
One more in the
Al,
chat. Oh,
from Hank, yeah.
Yeah, it's here. Serve claims we need a much higher ventilation rates. Thoughts? Yeah, I think Alex is going to respond to that very well. It's a complex topic. You don't need a whole lot of ventilation to manage CO2 alone. But when it comes to the other household contaminants, whether it's some kind of VOC, disease, like we've all dealt with the COVID thing, the analysis gets much more complicated. And some people think that we can manage more of it with high MERV filtration and recirculating. Some people think we need more outdoor air. The jury's still out on it, at least from what I've read. I think hitting the FIAS recommended flow rates will cover a lot of the common indoor air quality concerns in single family, especially, and in multifamily, we're seeing pretty high air exchange rates from those same targets, and especially, or even just from the minimum requirements from EPA's Indoor Air Plus, the 20 CFM out of bathrooms continuous and the 25 CFM out of kitchens continuous. When you're talking about smaller scale apartments, that's a lot of ventilation, a lot of air changes per hour. It's not at like operating room level, but it's that balance between energy loss and indoor air quality that needs to be discussed there too. So jury's still out on that one. It's complicated. Yeah.
I think we got to switch gears because we still got a lot to talk about. I'm going to show a couple slides about renewables. So we also looked at, we've got quite a few options for renewable energy that FIAS allows to be used to offset the targets for total energy use. So on-site PV is still the most common. Quite a few of our projects don't necessarily need PV. All of them need to be photovoltaic ready as part of zero energy ready homes requirements. But they don't necessarily need it to offset the source energy target that we have for projects. They can do it with efficiency measures instead. So that's why you see a fair number with not applicables. RECs, or renewable energy certificates, are one of the offsite methods we have available for people to use to offset their source energy. And we can talk about that a little bit more. But basically, by project type, it's more common to see renewable energy certificates in multifamily projects. We're seeing it more frequently for projects that are, taller, much taller buildings where, the roof to area of the building ratio is such that you can put PV on the entire roof and then some, and it's not going to do that much of a dent in the overall energy use of the building. So renewable energy certificates are a way for project teams to basically purchase renewable energy and improve the grid. So, like adding more renewables to the grid rather than adding them directly to your building. So it's kind of a different way of attacking the problem of renewable energy. But I think it's it's effective as well, right? Like the more grid we have that's renewable, the better the system is going to be as a whole. So quite a few single family projects use on-site PV. Basically, it comes down to, okay, we met the space conditioning targets, and now we're going to use some funds to put a small PV array on our building. So we do see quite a few single family projects that have on-site PV. All of the school and education projects we had on this list actually is pretty interesting, have on-site PV. And I think all three of them are also net zero. So they've got enough PV to offset all of their energy use. All three of the projects we were looking at were in my backyard in the Chicagoland area. They were participating in a grant called the Illinois Clean Energy Community Foundation. So they all got grant money to get a quite sizable grant, I think between $1 and $2 million for a net zero project that was proven net zero after a year of occupancy. So all three of those projects were net zero, all on site PV. By project type, all of the retrofits we looked at also had on-site PV, which is pretty interesting that they're able to do that. One of the things we hear from some project teams when they're talking about, okay, why do we need to have our project be zero energy or be solar ready? We've got an existing roof. It's not going to have the structure to hold the PV. All the projects we saw for retrofits didn't have that particular issue. I know it could be an issue, if you got undersized roof joists or something like that. But that was also kind of interesting that, all the retrofits we saw had on-site PV, and the new construction ones were the ones that were using the renewable energy certificates. Let's see, let's go with, I think we're now talking about the grid. Were there any questions before we move to the grid and passive buildings about renewables in general? The grid is kind of tied to it a little bit. Otherwise, do you want to take it away on this part too, Al? You want to talk about this a bit?
Yeah, so as we all push to electrify buildings, we need to connect with the biggest machine on earth, which is our electrical grid. And this is going to be fairly a high level, and all of this is based on the work of our colleague Lisa White, who has been very committed to studying grid and grid interactive buildings and how passive house can play a role within that design. So there are essentially three big chunks of our grid in this country, and then there are also a couple other smaller ISOs, and those are all of your more localized utilities and energy providers. On the next slide,
well, even before you go past this, I think it's important to note that the grid that the US uses is interconnected with Canada's grid as well, right? So it's talking about the grid is not just your neighbors and stuff like that. It's also the neighbors to the north, and also I think Baja, just south of California, Baja, Mexico, and Mexico also is connected to the southern part of California's grid as well. So all of these are kind of interrelated, and I don't know. I think it's interesting to think of for the greater context of the grid in general.
Cool. Yeah. And so as we all, I'm sure, are familiar with here, the grid isn't always as clean as we'd like it to be currently, and it's getting cleaner, and it has gotten cleaner over the past couple of years. So this here shows that the highest growth in all of our grid production is the non-hydro renewables. That's solar and wind. While nuclear is maintained a fairly consistent 20% of our generation here, coal's dropped significantly from 40% down to about 20%. And we've seen a slight uptick of natural gas. So this is where the grid mix sits currently. But at the same time, if we go through and electrify a lot of buildings, we're going to increase the demand on the grid. So we're going to need to make sure that the growth happens in the right area. And so NREL, our National Renewable Energy Lab in the United States, has gone ahead and made a projection of what they think our grid mix will be in 2050 based on current utility projects as well as any of the proposed utility projects going forward. The biggest chunk as well we see in this is that orange bar, which is the utility scale solar, tongue twister. And we're looking for more growth in that area. The pink line at the top is storage as well, which just like we've had a discussion with the solar water heating, we need a similar level of storage on the grid to be able to maintain, to be able to charge up batteries or maybe pump water up a hill. There's many different storage techniques to allow for us to have that capacity when we need it, rather not when the sun is shining or the wind is blowing. They're projecting a fairly a decrease in coal and a slight decrease in nuclear. So overall, by 2050, our current grid mix, we use a source energy factor of about 2.8 to reflect that. Our projected for 2050 is 1.8. So we are seeing the grid get cleaner, and it's projected to get even cleaner. On the next slide, we can talk a little bit about the profiles the grid experiences. So pretty much all of the grid throughout the United States experiences a peak demand in the morning and a peak one in the evening. So that's everyone getting ready for work and everyone returning from work. So we're able to maintain consistent base load to keep everything on that needs to be on. There's some intermediate generation sources, so like natural gas and some renewables, we're able to meet that intermediate load demand. But when it comes to making peak power, where we experience these high peaks in the grid, that's where we need any type of a natural gas peaker plant or some hydro where we can throttle it. So nuclear is a good base load source. It's not highly throttleable, but natural gas and hydro are better to manage those peaks because we can turn them on and off quickly. And on top of that, the use that we make at those peak points is also our most expensive energy cost per kilowatt hour. So renewables tend to be the cheapest, and those quickly rampable type gas turbine power plants are the most expensive to operate per watt. So trying to reduce those peaks, which is also going to is sort of the goal that we need to have looking at this grid projection. On the next slide, we have anyone who's looked at anything involving the grid will notice the infamous, they call it a duck curve, and that's the belly of the trough there, which is when we've got, so this is California. So the duck curve is met by this solar curve, which is the inverse of it there. So there's during the daytime when we have our lowest demand is when we have our highest solar production. And that's why we see this ramp at the end here, which is back when everyone comes back on and is turning on their systems as they get home from work. But that's also when we see the drop-offs of solar. So that's where that peak is coming from currently. But going forward, this is going to end up having to require system level thinking, because any of the decisions we make at the building level impact things that happen at the grid level and vice versa. And all of this needs to be an interconnected solution if we're going to be able to decarbonize the building sector completely. So what are the current challenges and things we've been able to use? So in the decarbonization movement, we have the concept of net zero buildings, right? Make as much energy as you use. We have the need to the strong push to electrify, and we're seeing an upswing in equipment and technology to electrify current building systems that we typically see, like the replacement of gas boilers with the CO2 heat pump for centralized domestic hot water. And then also, how are we going to get more dispatchable fossil fuel based power generation? So any of those peaker plants, how can we shift that to use electricity either made at a different time and stored, or can we integrate our demands, or can we shape our demands to match when we have renewable energy as our peak production? So passive buildings, we think, and are going to play an important part in this. We're able to take those typical peaks, and so this is in the typical building, you've got high peaks in terms of heating energy and cooling energy, and then the area under this curve is going to be the total consumption. But by making a passive building, we're able to reduce those peak loads and therefore also reduce the area under the curve. So smaller peak impact on the grid, as well as smaller overall annual consumption for space conditioning, which is the biggest load in a lot of these buildings. And on the next one, well, this is that these are the peak PV production. So with the baseline building, there's the building load, and all of that production happens at the middle here. And we're seeing an increase in colder climates where the increased load exists more, especially in the morning and at night, in terms of trying to keep it warm when there's no solar gains on a baseline building. If you're doing a passive building, the blue line, the total building load, is a little bit more stable throughout the day, and it's much lower. So instead of pulling 50 kilowatts or 50 kilowatts as a peak, we've pushed that down to below 50 in both cases. So we're able to reduce the total PV production we need because we've reduced the annual demands, as well as we don't need as much peak PV production because we've reduced those peak loads as well. So going forward, we think that there's going to be more need for a grid interactive efficient building, or a GEB for more acronyms in the building science lingo. And essentially what that is there's, on the next slide, I've got a little diagram here. So all of the controls for what happens within a building will need to talk to each other at a smaller scale, whether that's a microgrid and that's connected to the bigger grid, or anything or like that. So currently the controls in a grid only go one way. The utility sees the demand for electricity and responds accordingly, but the utility can't communicate to buildings to manage their load. So that's where this smarter level of control for the grid interactive building comes into play. And the two ways they can do that on the next slide are load shifting and load shedding. So with a load shift, you've taken a same load that you might have. So for example, domestic hot water heating, and we're going to make that during the day when we've got solar and it's stored in a tank. So we've just shifted it to a different time of the day to reduce a peak. And then there's a load shed, and that's the super insulated passive envelope. So it's going to pull down those peaks because we just don't need as much energy to heat a building because the envelope is doing more work. So shift is take the same load to move it. Shed is eliminate that completely. So yeah, this is that, like I was talking about. So the signal traditionally is only flowed the one way. So with this, what we can do with the GEB is we're able to, at the same time we're sending power to a building, we can send a signal to the customer that they need to reduce load. So they need to have some kind of demand response. So that's where the building will either do a load shift or a load shed based on its current conditions. So on the next one, yeah, so this is how that passive building works in that regard, is there's an inherent thermal storage within that building envelope that's able to keep the peak loads down and move them through the day. So you could, for example, California just had their they had some high peaks during those hot days, and they talked about setting the thermostat higher. So that would be a load shed, because you're decreasing the peak load that you have on the grid. But if the buildings were all able to pre-cool, so during the day when we had solar, some buildings would pre-cool themselves before everyone got home, so not everybody turned on their air conditioner at once, and you had the super efficient building envelope to keep all of that cool in the building, that's when you get the load shift. And if you stagger that, then the sum of those peaks is lower. So this is all stuff that we have to think about when we're thinking about building electrification. And so, for example, like we've mentioned this out a little bit here, if there's some kind of a storage for water heating, that's a significant asset in terms of that. So you can ride out times with less energy supply. And then if we electrify buildings as well, and we electrify all of the systems in the building, currently the US experiences its peak electric load in the summertime, because most of our cooling is electric, but our heating is not. So on the next slide, we're talking about that the peak will now become a wintertime peak when we've got less sun and less solar. And we've got these higher peaks to deal with. So if we go to eliminate those space conditioning loads, we're actually able to push that winter design load down by about half in colder climates. And so when you add up all of the coincident peaks of typical operation buildings, so if every building uses 4, just for easy math here, 3 buildings together have a peak coincident grid load of 12. Well, if all of these buildings were passive buildings and we're able to have half the amount of the next slide there, James. If all of these buildings were passive buildings and we reduce their peak loads by half, the 3 of them add up to only 6. So that's half the amount of initial grid load that we'd have if we were to just electrify buildings as they currently sit, our code minimum buildings. And then if we were able to include some good interactive control there to allow for preheating or pre-cooling a building at certain times, and we're able to shift all of those peaks so then instead of being coincident, they're spread out at different times, we could even reduce it significantly less for the total grid load. So business as usual, if we just electrify everything as is, we have a significant increase in electric grid load. With passive building, we're able to taper off the peak in grid load. And then if we're able to include a grid interactive building strategy, we can taper this as well. And all of that builds up to reduced transmission capacity and reduced solar capacity and reduced storage capacity. So by investing in the building envelope first, we can reduce the total investment needed at the grid scale to respond to our electrification needs. So that's I know this is a lot too, but that's just a brief summary of how, when we're thinking about mechanical equipment and renewables as a larger type setup and electrification of buildings, how this is going to end up impacting the grid and what the projected technologies are to respond to that.
Any questions? I'm sure there are some. There was already one in the chat from Hank about what states or utilities are leading in the development of Qav systems. And right now, I think California is probably leading for sure in terms of the Qav initiatives. They have really granular data on their current time of use for their whole grid, and they track it pretty well. And I think Texas and Colorado are also having some initiatives, not necessarily GEB yet, but the time of use discussion is very important for Texas and Colorado as well. Obviously, because they're, but Texas is a cooling dominated area, has, pretty incredible peaks when people come home from work, and in the middle of the day, the peak loads are pretty high. And because they have a ton of renewables as part of their grid, that, as Al described, were kind of the baseline only, not really used so much for the peaks. That's why their time of use is pretty important in that state as well. Yeah. Any other questions about the grid in general? And how passive buildings fit in? I think we have a little bit of time for that, because we got through this faster than I thought we were going to, Al. Good job. Right, perfect. Everybody knows everything they need to know about the grid. That was our, that's what we have for you guys. I think if, general questions on the whole thing, I think we're totally open to. So any other mechanical systems you guys want to discuss, or hot water systems, or anything you guys have seen on projects that you're curious if we've seen, we can definitely walk through. But yeah, this is what we had for you guys for mechanical stuff.
So I have a question. So I have a friend, I live in Boston, and she has a maybe 1,200 square foot condo on the second floor. And the Mass Saves program just sold her 5 heat pump units, basically one for every room in her house. And there's no insulation, and that is not the point, right? Like to basically overdo it. And that, to me, it seems like they were just selling it to sell it. They weren't really considering the full impact. And I'm wondering if you guys have seen that, and how, what do we do about that? I don't know.
May I respond to that?
Go for it, Alex.
Yeah. Hello all. It's good to see you again. Hello, Kylie. So unfortunately, it's still a rule of thumb for a lot of HVAC contractors to suggest oversized equipment. Okay, and obviously some of them are making more money selling you more equipment or larger equipment. And that's a pity. But there's nothing much we can do for now regarding that. But again, I don't have the specifics of what kind of sizing those 5 heat pumps are. Maybe they're very small, but still 1,200 square feet. Even if it's, how old is do you know how old is the building?
It's an 1894-ish.
Yeah. Okay. Well, it's with no re-insulation whatsoever. It's a leaky bucket. So yes.
Yeah.
So not surprising. It's just that logically, what we'd like to see in a retrofit is, okay, it's always money well spent to have a professional to do a precise calculation of the loads. Okay, and we've seen that for too many years that rule of thumb, we're going to put X amount of done per size of this house and that house. But as we know, in passive house buildings, we cannot do that. We're going to have some issues, as we know. So yeah, so in the case of retrofit like that, it's kind of important to do that too, and to make sure that they're going to have the right size kind of equipment. Seems logical and obvious for most of us here, not all of us, but unfortunately, the mechanical industry have been around since 2006. When back in the days I was working for Fantex System, selling HRVs and ERVs up here in Quebec. Well, yeah, it is a good industry, but there's a lot of people who still carry around those old mentalities and those old ways, and they don't do much calculation. Unfortunately, also there's a lot of work. There's less and less people to do the work. So some people may, in some cases, may be forced to cut corners and use some good old rule of thumbs. So I'm sure your friend is not missing either in cooling. It's just that is it efficient? At the end of the day, probably not. But I don't know. I do not have all the specifics regarding that. Yeah, that's my 2 cents. my long 2 cents.
Yeah, and I think to speak to it from the point of view as well of, like incentives being out there that have, good intentions at heart, but not necessarily having the whole picture together, right? Like if obviously they think they're doing a good job by incentivizing and saying, okay, we're going to make this, all electric, that's the way we need to go. But that's kind of exactly what we're showing in this condition, right? Where, okay, if you make all the existing buildings all electric right now, like tomorrow, obviously that's going to be a huge load on the grid that's not going to be manageable. So it's basically what we're trying to combat, those types of scenarios where you're severely oversizing a system, and purchasing a lot more stuff than you necessarily need to if you were to do it in a more thoughtful process of getting the building to reduce the loads first, and then you're meeting it after.
Yeah, as we know, the best energy is the energy we are able to say, right? So James, you said something that made me thought about something else regarding that. Oh yeah, well, ultimately, your friend is not using gas anymore, but to be efficient is also important, because if you're using, I don't know, 50% more electricity that you should for your real needs, well, the electricity, especially in the United States, the sources where you get your electricity is compared to us here in Quebec, where it's 99%, hydropower, which is renewable. Well, if you have, electricity done by a coal plant or gas plant, whatsoever, well, okay, you were efficient in your house, but you're using kind of a dirty electricity. So it's, the bigger picture is, I guess, always more complicated.
For sure. And then Hank had his hand up. Go ahead, Hank. You got a question?
Can you hear me?
Yes.
Yeah. So the example that you just gave regarding the heat pumps for retrofits under the Mass Save program, that is exactly the kind of situation that for the last 2 years I've been lobbying the EAC and Mass Save to try to change. They need two things. At a minimum, they need to marry deep weatherization with heat pump installation. They have a disconnect between those programs, and they claim to be trying to move in that direction. But without it, it's a disaster. I mean, not only is it a disaster for the grid in terms of how much electricity it's going to take to heat that 1890 building, but it's a disaster for the resident who's going to pay the bills, the electric bills for that. Assuming they put in enough heat pumps to make them comfortable through a deep winter, they're going to be paying exorbitant amounts of electric bills. And we've been pushing the Mass Save for a deep energy retrofit program that, well, maybe it's going to happen, but stay tuned to Passive House, Massachusetts. We have updates on our lobbying efforts to try to get a deep energy retrofit program in place. We're lobbying Mass Save directly, but we're also lobbying the legislature for a zero carbon renovation fund. And we're asking for $250 million to develop prototypical pilot programs for decarbonizing through deep energy retrofits multiple building types. We need to get going. Our climate bill, which is a law, says we need to do deep energy retrofits on 1 million buildings by 2030, and we've done less than 1,000. So we've got a little work ahead of us.
Right. And then I think you had a question in the chat too, Hank, about electric vehicles and the role in storage and the GEP structure. And I don't know a ton about how that interaction works, but I do know electric vehicles are for sure the future, right? Like, I don't know. I saw the Super Bowl halftime, all the commercials during the Super Bowl. I know electric vehicles are here like right now. So I did just want to put in one note that I did also, I didn't have a chance to put it in graph form here, but basically all the projects we looked at, I think like 80% of them had either electric vehicle readiness, like they had conduit in place, getting ready to put in a charger, or already had a charger in the building. And that was across the board for both the multifamily and the single family projects that were in this group, which was I mean, it was good to see. We didn't start requiring that until FIAS 2021 to have it electric vehicle ready. But even on the 2018 projects, we saw a fair number of them already had it in the plans that they were doing that of their own volition, because, you know, they could kind of see the change coming soon. There is one more question in the chat as well. So someone had mentioned at the end of the last presentation that new guidelines for passive house certification would be CPHC verification of the project's construction. I'm wondering if I mistook what was said. I interpreted what was said as the FIAS certified reviewer had been removed from the process. So FIAS is not moving that direction. I'm not sure. I can't remember exactly what was said. I know that was only 2 days ago, but I can't remember for sure what was said. But I mean, definitely the CPHC is still crucial for the design. I think the on-site project stuff, though, is still done by verifiers and raters for the most part. And then FIAS's role for the on-site quality assurance is to review that documentation. We still definitely have projects go through the design and final certification processes at FIAS at the moment. That's the intent for the future as well. Do you have another question, Hank? Go for it.
No, I think that question came out of a comment I made the other day, which is that in Massachusetts, when we put passive house in as an alternative method for energy calculations, and now we have it built into our new stretch code coming up. The point I was making was that we set it up so that for a building permit, you need a CPHC to show that the pre-certification documents have been submitted and state that they are in compliance with the plans they've reviewed. We don't need pre-certification from FIAS or anybody else to get the permit issued. That would be too potentially a bigger hangup. And even more importantly, on the other end for occupancy permits, we have to have a situation where we can't be calling up James Ortega saying, James, if we don't get that goddamn final certification, we're not going to have an occupancy permit. So we have to set it up. What we did do is to set it up so that the same CPHC can certify to the building department that they've looked at the final documents, overseen the final construction, taken the information from the raters and verifiers, and will say that this meets the requirements, even without the final certificate of compliance from FIAS. And that's critical because the missing a building occupancy date for an affordable housing project is a financial disaster. And if I were doing the project, I would avoid certification just for that very reason of being scared to death of missing that because of that type of certification. So that's what we built in order to accomplish both things.
And it looks like per that section, it's an either thing, right? You can either do that route, or if obviously if you have design certification in hand, that's another, you know, if you were ahead of the game, that would also be accepted.
Yeah, absolutely. If you have it, excellent.
Yeah, thanks, Dan. You for putting that link to that language in the chat. That's super helpful. Let's see. Any other questions in the chat that we can answer? Al, have you seen any in there?
There was a question about an online service to check heating and cooling loads for sizing equipment. I've been on a hunt for an online or affordable version of Manual J for a long time and have not found one that I like. So sorry.
Okay,
Sorry.
thanks.
Yeah.
I asked that question. I appreciate that. I recently used a service from a company down in Virginia that was recommended by Efficiency Vermont. And it was pretty good. It wasn't that cheap, but I thought it was pretty good and it was a good way to check. I think it was the fee was $500 and we sent them our documents and they sent over the calculations. And I was just wondering if anyone else had any suggestions for that.
Yeah, there's a question in the chat, Catherine, for what company was that you went through?
I'll have to look that up and I'll put the link in the chat.
Thank you. Yeah, Alex, good point. Yeah, liability issues. It's hard to find it for free online.
Yeah. Okay. I think one other thing on Hank's question about the cars, the electric cars. I've done a little bit of a back of the so we're going to display the CEU code now. So write that down so you can self-report. But I've done a little bit of the back of the envelope calculation in conjunction with some energy modeling. And for example, the new F-150 Lightning has 130 kilowatt hour battery in it. And you can probably use about 80% of that with the lithium iron phosphate. So you're talking about 110 kilowatt hours, and a passive electric building in the wintertime, single family home, 2,200 square feet, is probably going to consume about 300 to 400 kilowatt hours a month. So based on the battery of the vehicle alone, you could run everything as normal operation for 7 days. I think we'll see more of that come in as we figure out the technology between like a two-way charger and how to use that. And it might be really good for a localized storage option for a load shift, where you can charge the vehicle during the day and then suck from it at nighttime if you need it to manage your grid peaks. So it's coming. It's coming. I think we trying to fine tune and optimize that strategy needs work still.
For sure. And I think with that, we'll give one more plug for FeesCon coming up in Chicago at the tail end of October. You can come join us. You can ask any other questions you have after you have a chance to absorb some of this stuff that Al and I talked about. Al and I will both be there, and we'd love to see you too. And yeah, the Catherine has thrown the name of that company in the chat, Energy Vanguard, for the heating sizing.
Allison Bales Group.
Allison Bales Group. Yep. So
yeah, they were great. It was for a passive house. They were like $500 for the fee.
Yeah, it's not bad at all. Okay, Aaron, I think we wrapped questions. I don't know if we're allowed to wrap up 5 minutes early, but we're there, I think.
No, that was fantastic. Yeah, I'll let you go. James, Al, thank you so much for putting this all together. Today's presentation and Tuesday's incredible information to kind of see all of this data and have it presented in this way. So we really appreciate it. Everybody for being here. Thanks for attending it. Thanks for asking some good questions. We will get a recording of this session up as well, so you guys can have it for reference, along with the session from Tuesday. The FIAS code there is for today's session, and I'll try to get the one from Tuesday's session up as well, but please email me if you can't find it. I'm happy to help you all. So thank you for being here. Take care, and we'll see you all in the future.